Hello, welcome back AP Physics students. We are starting Unit 8, which is on waves, vibrations, and simple harmonic motion. So I actually made this animation. If you can look at it carefully, or you can't really see, but it's made of a bunch of ellipses that are simply rotating at an offset time. And that's how the wave is created there. But anyway, so this unit again is talking about waves and vibrations and oscillations and things kind of repeating back over and over again. Every atom in your body is vibrating. It's part of its rotational. It's part of its energy state. Would this be a type of energy? Sure, it is. Okay. We can see that it's kinetic energy, and then some kind of potential energy would be involved too if this were atoms, some kind of the chemical bond energy. So or electrostatic energy. But anyway, vibrations and waves have energy and can move it from one place to another. It's a way of storing energy, and it's a way of moving energy from one place to another. If we look at a basic wave, one complete cycle, so this is a sine wave. Is this a sine wave? Opposite, I think so. Yeah. So one complete cycle is an up hump and a down hump. So I've got one shown in blue and one shown in green here. So when we talk about one cycle, that's what we mean before it repeats itself over again. If we were to draw a line through the middle of the wave, that would be what's called the baseline. That cuts the wave in half into the up humps and the down humps separately. The top or high point of the wave is called a peak or a crest. The low point of the wave is known as a trough. And where the wave crosses the baseline is known as a node. So that's some terminology I would like you to be familiar with. The length along the baseline of one complete cycle is known as the wavelength, and we use this upside down Y looking character. It's a Greek lambda, and that's the symbol that we use for wavelength. So take a look at that. And we can think of it as the length of one complete wave, which is the same as the distance from trough to trough, which is the same as the distance from crest to crest. So that's all ways of measuring the wavelength. The amplitude is the distance from the baseline to a peak or crest, or from the baseline to a trough. Okay, they will be the same in the waves we're looking at anyway. And that's again known as the amplitude. So it's basically the height of the wave, but it's not from the tippy top of the wave to the bottom of the wave. It's measured against the baseline, so keep that in mind. So if we were to look at these two waves, these waves have the same amplitude or wavelength. They have the same wavelength. So the same wavelength, but they have different amplitudes. Okay, and these waves, okay, have the same amplitude, okay, but have different wavelengths. And again, notice there we measure it from crest to crest. That's another way of measuring the wavelength. Now, when waves are in motion, we can start talking about the period, which is the time it takes for one complete cycle to pass by a fixed point. And we can start talking about velocity and frequency and different things, but we're just concerned about the period for right now. So basically, if you were to start your stopwatch when a wave reached the measuring point, and then if you ended your stopwatch when that complete wave ended, then you'd measure the period. So it's just the time it takes for a wave to pass some point. Okay, similar to period, but not the same, is the frequency. The frequency is the number of waves that pass by a point in a given second. Okay, so it's the number of waves per second. So in my example here, 2 waves pass by this point in 1 second. So it would have a frequency of 2, what's known as hertz. Okay, 2 cycles per second, which is also known as a hertz. So If a wave has a period of 0.25 seconds, that means it takes a fourth of a second for a wave to pass by a fixed point. How many vibrations are going to pass by that point in 1 second? If it takes a fourth for 1 second, I'm going to be able to fit 4 of them passing through there in that same second. So what we really did there is we just took the inverse. So the frequency is equal to the inverse of the period. And the symbol for period is the T, capital T. So time is a lowercase t, period gets its own letter, it's capital T. And frequency, the symbol in the equations is just F. Okay, so F equals 1 over T, or T equals 1 over F. Same deal. Okay. So when we talk about frequency, when we figured it out before, it was in cycles per second. Normally the term cycle is left out, and it's just 1 over seconds, or seconds to the minus 1. You might see the symbol written like this, seconds to the minus 1, and that of course just means 1 over seconds. But the nickname for that is the hertz, and the abbreviation for hertz is capital H, lowercase z. So frequency is measured in hertz, and it's the number of waves that pass by a point in a given second, or the number of oscillations that occur per second. Radio, your radio dial, which I'm sure aren't dials anymore anywhere, hardly anymore anywhere. But when you dial into a radio station, if you still do that, 93.3, which used to be a station I listened to, I don't know if it is anymore. What that means is that's actually measured in megahertz. So 93.3 megahertz is the frequency of the radio wave that's bringing that signal. And so 93.3 million waves pass through your antenna per second for that frequency of radio station. AM is measured in kilohertz times 10, so it's those are typically lower frequency radio stations. So we're going to be looking and applying a lot of what we learned to waves, which we can think of as an ocean wave, vibrations, which we can think of as the atoms in your body, or two masses attached by a piece of rubber, or an oscillation, which would be an example of something swinging back and forth like a pendulum. They all have a period and a frequency, and we'll get into some other similarities and differences. So again, if I wanted to measure the period of this wave, what I would do is maybe wait till a high point reach the right point of the screen, and then start my stopwatch, and then end my stopwatch when the next crest reached the thing. If I wanted to measure the period of a pendulum, what I would do is say, let's say we're going to start our stopwatch when it reaches this right point. Okay, so next time it reaches all the way to the right, I'm going to start my stopwatch, and then wait till it comes back, and then end my stopwatch. And then you would do something similar for a vibration. Just start your stopwatch, and then wait till it comes all the way back, and then end your stopwatch. So this repetitive kind of back and forth motion or oscillation is sometimes referred to as simple harmonic motion. There's a little bit more to it than just simply a repetitive motion, which we'll get into in a little bit. But that's really kind of the topic of the beginning of this unit, is simple harmonic motion. Okay, so going back to our definition. So here I've got two vibrations, two oscillations, and if I were to ask you which one had the greater period, okay, which would you say? Well, period is the time it takes for one complete wave to pass, or one complete oscillation to occur. And this one is certainly taking longer for one oscillation, so it must be the lower one. Okay. Now, if I ask you which vibration had the greater frequency, well, frequency is the number of waves that pass, or the number of oscillations that occur in a given second. So this one is certainly going to have more complete oscillations, or more oscillations occur per second, because they're occurring more rapidly. So this one has a greater frequency. Okay. which one has a greater amplitude? Okay. Well, the period and the frequency are the same because they're occurring at the same rate. The amplitude is, you can think of that distance from the baseline, how far out it goes. So it would be this upper one. Okay. So if we were to hang a ball on a spring and let it stretch, it would reach down to a point where the forces on it were to balance, and this would be known as the equilibrium position. So right now we let this stretch, and it's going to reach that equilibrium position. Okay, so at the equilibrium position, there's no net force on the ball. The force of the spring pulling up is canceled out by the force of gravity going down. Okay, so all the forces are balanced. Now, as I stretch it, okay, the force on it's the net force on it's going to increase. The force from the spring is going to increase, and it's going to be trying to pull it back. So when I let go of it, it's going to accelerate. And as it accelerates, that net force decreases when it reaches the equilibrium position, or as it reaches the equilibrium position. So then the net force on it here is 0 again, because that's the equilibrium position. Now it's going to continue past that. Okay, so here this is represents that ball on a string that I pulled and let go, and it's just oscillating back and forth. And I've got the direction of the net force and the magnitude of the net force on the ball listed or indicated by these little black arrows. And what you see is this net force always drives it towards the equilibrium position. So I've got, and this should look a lot like the baseline of our wave. Okay, that middle line, okay, and this would be kind of a crest, and this would be kind of a trough of this relationship. So when it's above the equilibrium position, the net force is driving it down, and when it's below the equilibrium position, the net force is driving it up. Okay, so here we've got this thing oscillating back and forth, and if I were to ask you, when does the ball have the greatest net force acting on it? At the ends or in the middle? Okay. Well, from the picture we just looked at before, and we know that it's going to be the ends. So it's got the greatest force acting on it at the very high point and the low point. Okay. Now, when does the ball have the greatest speed? Well, it's moving at 0. It's stationary for a split second at the very ends before it changes direction. So it's certainly not going to be the ends. Okay. So it must be moving the fastest in the middle before it changes direction again. Okay. When does the ball have the greatest acceleration? Well, okay, its net force is 0 in the middle, so that means it's got 0 acceleration in the middle. Okay, and it's got the greatest force acting on it at the ends, and force equals mass times acceleration, so it's going to have the most acceleration at the very ends. Okay, so in simple harmonic motion, if the object is not at the equilibrium position, there's always a force driving it towards the equilibrium position, and that net force that's doing that is called the restoring force. And so here I've got the restoring force indicated by the black and blue arrows. Okay, and the restoring force gets stronger the further you are away from the equilibrium position, and it's the greatest at the high point and the low point. Okay. Now, the object is moving the fastest in the middle at the equilibrium position because it's been accelerating all the way down, and as soon as it flips to the other side, the force flips to actually slow it down. So it's slowing it down as soon as it crosses the equilibrium position. And that is it for the notes for today. If you have any questions, see me at the office hours.